Hello, this is Mr. Antrim, Chemcast and Thermochemistry. We have already studied some thermochemistry in Chapter 6. We've looked at how to solve calorimetry problems and Hess's law problems. In this Chemcast, we're going to look at how we can use something called heats of formation to determine enthalpy of a reaction. Enthalpy of formation, given this symbol delta HF with the superscript of a 0, simply is the amount of energy that is absorbed or released when 1 mole of a substance is formed from its constituent elements. For example, the delta HF for water is the energy released when 1 mole of water is formed from its elements, hydrogen and oxygen. So the heat of formation, the formation is relating to the production of, in this case, 1 mole of a particular substance. The value for the heat of formation of water is negative 285.8 kilojoules of energy. Again, that's the amount of energy when 1 mole of water is formed from its reactants. I refer to this as standard enthalpy. In that we're measuring the conditions at standard state. Standard state is not to be confused with STP, for example, in gases. Standard state relates to the most stable form of the substance at 1 atmosphere and 25 degrees Celsius. So the little superscript 0 there, anytime we see that, that refers to its change in enthalpy relating to the substances existing in its standard state. In other words, what state that exists at 1 atmosphere and 25 degrees Celsius. Water standard state, of course, is a liquid. Water is a liquid under these conditions. Oxygen standard state is a gas at these, because it's a gas at 1 atmosphere and 25 degrees Celsius. Copper standard state would be a solid, because it exists as a solid at these conditions. It's important to note that the enthalpy of formation of a free element is 0, and it kind of makes sense because you don't form an element. So, for example, the delta HF value for oxygen is simply 0. Here's a table of delta H values, again at standard conditions. And you notice a lot of variation. One of the things I would like to point out, look at some of these substances that have very large negative values. That would mean a great deal of energy is released when 1 mole of sodium carbonate, for example, is formed from its elements. If we reverse that reaction, we could look at that as an indication that sodium carbonate is a very stable substance, because it would take over 1,000 kilojoules of energy to break it back down to its free elements. Whereas a substance such as acetylene has a positive value, which indicates that energy is actually required to produce it. So if we break it back down, it would be exothermic and would release energy. Once again, we see for free elements, these delta HF values are 0. Oxygen as a gas, its state exists as O2 molecules. So the heat of formation of oxygen atoms as a gas does have a value, because it does take energy to produce oxygen atoms in a gaseous form compared to its freely forming form state as oxygen O2 molecules. So here's the equation that we're going to be using to determine delta H. Again, we saw how we can use Hess's law. We saw how we can use calorimetry to define the change in enthalpy, delta H. Well, here's a third way. It simply says, and you might remember this from first year chemistry, the delta H of a reaction is equal to the sum of the heats of formation of all the products minus the sum of the heats of formation of all the reactants. The N and the M are the coefficients coefficients in the balanced equation. Again, this is very valuable, we will see, for determining thermochemistry for a particular reaction. It's usually faster. We just simply look up some numbers and carry out a calculation, faster than conducting an actual original calorimetry experiment, for example. It's a very important reaction. And here's an example. Let's look at a combustion of propane. When we're burning propane, we see that propane, a hydrocarbon, reacts with oxygen. We have a balanced equation. Combustion, we always release carbon dioxide and water. Of course, if you recall, when you see a flame from combustion, you're simply looking at the very excited hot gases of carbon dioxide and water. So what we need to do, if I want to find the amount of energy produced from burning 1 mole of propane, I'm going to use our delta H equation that we saw in the previous slide. So we see 3 moles of CO2. We would have to look this number up. These numbers are given in a chart in your textbook. Plus, because it's the sum of the products, plus 4 moles of the heat of formation of water, which we'd again look up. And we're going to take that entire term and subtract it from, as the definition says, the equation, subtract it from the sum of the heats of formation of the products, or sorry, the reactants. So in this case, we have 1 mole, and look at the heat of formation of propane. Notice we don't include this because the oxygen would be have a 0 value. You can go ahead and include it, but it's not necessary. When we do this calculation, it turns out that the heat of reaction for this is 2,220 kilojoules, which would mean that if we burn 1 mole of propane, we can produce that amount of energy. This happens to be a special type of delta H known as heat of combustion. It's also sometimes designated as delta HC, subscript C for combustion. You need to practice some of these on your own. So if you want to pause and try doing determining the heat of combustion for octane. Octane, main ingredient in gasoline, C8H18. And again, carbon dioxide and water would be the products. You can check your answers in a moment. You can also like you to try to explain the difference. Why is the heat of combustion for octane so much greater or significantly greater than the heat of combustion of propane? And also consider, and these are things that you should be prepared to discuss in class, how would this type of calculation be useful? And one other item to note here, if propane produces less energy than, for example, burning methane produces less heat than propane, why do we use propane in our homes to heat water and maybe heat the air in our, from our furnaces? Why not use propane if we can get more energy out of propane than methane? So again, we will just be prepared to discuss that in class. Here's a list of chart of heats of combustion for a number of fuels. There's methane, natural gas, and using that energy to heat our homes, or heat the water in our homes at least. A lot of sometimes we use propane in a propane tank, butane, for example, in a butane lighter. There's the octane that we looked at for the previous on the previous slide, and methanol, ethanol, a couple alcohols, and a couple other organic compounds. These are all heats of combustion. Here's a special case, an application. It's just finding heat of formation if you already know the heat of the reaction, in this case heat of combustion. So I just want you to look at this. You can pause it and study it a bit. But in this case, we are given that the heat of combustion for propane is the 2220 value. And if you're given the heats of formation of carbon dioxide and water, of course oxygen would be 0, this question is asking you to find the heat of formation of propane. Okay, now in the previous problem, we actually calculated the heat of formation of propane. So in this case, we have a different set of information, and we're trying to use some values to calculate this particular value, the heat of formation. So we set up our equation, the delta H of a reaction, and it's again products minus reactants, but in this case we know the delta H value, so we just substitute and solve for the delta H, or sorry, the HF value for the propane molecule. So you can look over this calculation. You'll be expected to do this type of calculation on your own. Some more applications. How about some rocket science? Space shuttle, which is now, they've flown their last missions, but the science behind it was incredibly involved, and a lot of chemistry was involved in generating the energy necessary to get this extremely heavy object into orbit. The space shuttle orbiter, that's what the payload was in and what the astronauts were in, the cockpit there. The primary reaction when the orbiter is in space to maneuver it, to make small maneuvers, it doesn't have the engine supply anymore, so it just has small little reactors at various places on the body of the orbiter. And these reactions, they're called thrusters, provide the propulsion to maneuver the orbit and change its altitude or slow it down so it can re-enter. But the reaction is fairly complex, as shown here. And again, this is the reaction in the little small thrusters that provide the energy to maneuver the orbiter when it's in space. So if you look up all the values, you'd use your textbook, plug them into the equation, and you'd get this amount of energy. So at some point, some chemists at NASA or a contractor to NASA developed the thrusters and had to come up with a chemical reaction that would be efficient and provide the energy for maneuvering the space shuttle orbiter. The main engines, the actual engines that are responsible for getting the shuttle off of the ground, we see here, huge engines, and what they use is simply hydrogen and oxygen that's in what's called the external tank. Huge amounts, tremendous amounts of liquid hydrogen, liquid oxygen are in the external tank. They're pumped through the shuttle into the main engines, which are ignited, and produces a tremendous amount of energy, enough to, again, provide the thrust to help get the space shuttle off of the launch pad and into orbit. So there's another problem for you to solve, calculating the delta H for that reaction. And one more reaction, you notice, you don't see the exhaust from the main engines right here. You see a lot of exhaust coming out of these. These are called the solid rocket boosters. But do you know how you can't see any exhaust coming out of here? Well, if you think about the reaction that we just showed, the reaction produces water vapor. So you don't really see any of the product coming out of these main engines. But again, back up on that. The primary, the secondary reaction, these solid rocket boosters. Here's the reaction: aluminum and ammonium perchlorate was found to be a very exothermic reaction, and it produces aluminum oxide, nitrogen monoxide, and water. And that's what we see as products coming out of the solid rocket boosters. So one of the problems that you're assigned in the text is to actually solve the delta H for that particular reaction. Once again, chemists helped develop these processes for our space program. So the white exhaust probably is mostly little particles of aluminum oxide. Solid rocket boosters were actually, when the shuttle was flying, these would